Hi everyone, Professor Moser here. One of the things I wanted to talk to everybody briefly about was something that came up in the homeworks. This was related to critical scores. In our hypothesis testing, so this applies throughout all of Chapter 7, one of the things that we know is that we're using the p-value approach to hypothesis testing. Nonetheless, there are a few questions in the homework, specifically a few parts, where they ask you to find a critical score. This is not something that will be on the next test, but since it did make it to the homework, I want to just kind of briefly talk about it. The other approach to the p-value approach that we are taking in the class for hypothesis testing is the idea of critical scores and comparing whether a calculated score, how it compares to a critical score, gives us yet another way we can make a decision whether to reject or to fail to reject the null hypothesis. If you wanted to compute a critical z-score, this is how it would be done. And this is also kind of a little bit of an insight as to why I prefer the p-value approach. For us, whenever we're using our calculator, we just have to choose the correct tail test. We don't have to worry as much about if it's left tail, right tail, or two-tail test. But essentially what's going to happen is this. If we have a left tail test, and you wanted to compute the critical z-score, it's simply going to be the inverse norm of alpha, 0, 1, where alpha is our level of significance. If it's a right tail test, also I should note too, by the way, that when you're computing this critical z-score for a left tail test, the value will actually be negative. So if you punch this into the MyStatLab, you actually want to include the negative sign with this one, because it's a left tail test. If we have a right tail test, then we compute the critical z-score by doing the inverse norm again of alpha, 0, 1. But for a right tail test, you simply have to change the sign of this. In a right tail test, the critical z-score should be positive. So just simply take whatever you get from this calculation and change the sign. And then lastly, this is a typo, but if you have a two-tail test, pay close attention. In a two-tail test, there are two critical z-scores, and they are found by doing the inverse norm of half of alpha. So you have to do alpha divided by 2, 0, 1. That will give you the negative of the two critical scores, and then we would also need the positive of the two critical scores. So it's really nothing new in terms of computations. We know how to use the inverse norm from before. For the left tail, it's just inverse norm alpha, 0, 1. For right tail, it's inverse norm alpha, 0, 1, and then remember to switch it to a positive sign. And then for a right tail, for a two-tail test, be a little bit careful here. It's inverse norm, but you need to use alpha divided by 2, 0, 1. What the rejection regions would look like if it's a left tail test, we have our critical z value, we call that z naught. If the computed test z statistic is less than that, in other words, if the calculated z falls in this region here, that would be a reject the null hypothesis. If it lands in the other region, then it would be the fail to reject region. On a right tail test, the rejection region is to the right of the critical z value. So if our calculated z is bigger than that, meaning over here, this is our rejection region. The decision would be to reject the null hypothesis. If our calculated z-score or our z-statistic ends up in this region, then the decision would be to fail to reject. And then lastly, if we have a two-tail test, again, we have two critical values. We have the negative of z naught, the positive of z naught, and the rejection region is going to be the tails again. If the calculated z statistic ends up either here or here, we would reject the null. If the calculated z statistic ends up in this region, we would fail to reject the null. As an example, one of the questions you might see on the homework would be something like this. They say, find the critical value and the rejection region for the z-test with a level of significance alpha. Include a graph with your answer. Here is a two-tail test with alpha equal to 0.06. So we would go to our calculator. I'm going to go to the stat menu. Actually, no, we go to distribution. So second, vars, that's the distribution menu. Go down to option 3, inverse norm. And if it's a two-tail test, then it's going to be alpha divided by 2. So this would be 0.06 divided by 2, 0, 1. We go ahead and hit enter, and to 2 decimal places, this would round to negative 1.88. Because it's a two-tailed test, we have two critical z-scores. One of them is the negative 1.88, and then comma, the other one would simply be the positive of that, which is the positive 1.88. That means that the rejection region, if you were to draw it on the graph, would be anything that's less than the negative and anything that's greater than the positive. And from our chart just a little bit ago, this is what the shaded rejection region would look like for a two-tailed test. If it had been a left-tailed test, then it would have been like a chart like this. And what you're looking at in this example answer C, that would have been a right-tailed test rejection region. The other thing that can come up too is if you need to find the critical value for a t-score. The thing that's really convenient about the t-score chart is it actually breaks it down according to your tail. One tail is alpha, or two tails for alpha. If you're using a left-tailed test, then you would look up the one tail, and then just remember it has to be a negative sign. So in both the left tail and the right tail, those are just a singular tail. So you're going to be using this this row right here. If it's left tail, just make sure you have to choose the negative sign. If it's positive, if it's a right tail test. So for example, if I wanted to do a left tail test that had 5 degrees of freedom with an alpha value of 0.05, first thing I would do is I'd say, okay, it's a one tail because it's a left tail. So I'm going to be looking off of this row. I go till I find an alpha value of 0.5, which is here. And then I go down that column until I reach 5 degrees of freedom to put us right here. That value is 2.015. Now, because it's a left tail, I need the negative of that. So the critical t value in this case would be negative 2.015. If I wanted to do something similar, but let's suppose we have a right tail test, 5 degrees of freedom again, and an alpha value of 0.05. If it's a right tail, then once again that's one tail. 0.05 is here. I'm going to go down till I hit 5 degrees of freedom again. And because it's a right tail, I just use the value as it appears in the table. So keep it positive. The t value there would be 2.015. And then lastly, let's suppose we wanted to do a two-tailed test with 5 degrees of freedom and a level of significance of 0.05. Now this time we need to go down to the second column. This is the two tails, alpha. We scroll over until we find the level of significance, 0.05. And then we need to go down until we find 5 degrees of freedom, which would place us right here. So we have 2.571 coming from the chart. Because it's a two-tailed test, there's going to be two critical scores. One of them is going to be the negative of that value, t equals negative 2.571, and the other would be t equals to 2.571. So again, in the lectures, the critical t-scores wasn't something that we focused on since we did the p-value approach. What I will do is I still have to leave those as part of the question because they are built into the MyStatLab homeworks. But I will go through and I'll give everybody credit for just the critical score portions of questions. However, if you're able to answer them correctly, then I will kind of treat it as some bonus points that will go towards your homework average. Well, that's it. If you have any questions, everybody, just let me know.